Okay, so where are we on the timeline to Q-Day? And so for Q-Day to happen, we need what's called a cryptographically relevant quantum computer, or a quantum computer that's big enough, fast enough, good enough fidelity-wise to crack algorithms like RSA. So where are we in that timeline? So with every advancement in both theory and hardware, we get closer and closer. And when you ask experts in the field about when they expect a CRQC to be available, that timeline can vary. And we've heard anywhere from 2 to 3 years to 20, 30 years. No one really knows. But with every advancement on the theory side and hardware side, that estimate is shrinking. And when it comes to cybersecurity, it helps to put a lens of risk on this thing. So when you're thinking about timelines towards Q-Day and when to do this migration, look at it from a risk standpoint. If there's a 10% chance that a CRQC will be available in the next 5 years, is that risk appetite something you're willing to accept or not? So it helps to put that lens of risk on. Okay, so I wanted to highlight some recent advancements in both theory and hardware that are shortening the timeline to a CRQC. So I mentioned Shor's algorithm as the algorithm that is notable for quantum computers to break our asymmetric encryption and our public key cryptography. So what is required to run something like Shor's on a utility scale quantum computer? We used to think that this would take millions and millions of physical qubits. And recent advancements in quantum algorithm space have lowered those requirements. So both from more efficient error correcting codes, as well as variational algorithms like VQF and QAOA, where quantum and classical computers can actually work together to, for example, factor a large integer into its primes. So all of these advancements in theory really kind of reduce the requirements for a CRQC in terms of number of qubits, the fidelity of qubits we need, and the resources necessary for breaking something like RSA. So that's the theory side, and there have been many advancements in quantum computing hardware. And so these quantum computing vendors and manufacturers, they periodically release and update their hardware roadmaps. And we're seeing many of these announcements about modular quantum computers. And the idea here is that, we can only put so many qubits on one chip on a monolithic approach. And we saw the same patterns in high performance computing where, now we're going to deal with many processors working together in some kind of data center or networking system. So we're seeing these modular roadmaps. Of course, to enable a modular system, you're going to need interconnects between your processors. So IonQ recently this year announced a demonstration of an ion-photon entanglement, which is a critical step towards those photonic interconnects between processors. But other than those modular architectures, qubits are getting better. These systems are getting faster, more powerful. There are many different metrics you can look at for how you want to assess performance across these different vendors. But you can see the trends here that, quantum volume and other metrics are continuously increasing, as well as qubit count. And very exciting, there have been some demonstrations with logical qubits or, fault-tolerant quantum computers on a very small scale. But this is really promising for, reaching, utility scale or even CRQC scale quantum computing.